Alrighty, so purpose to show the net force for a conical pendulum is mv squared over r. So basically that's what we're here to do. We've talked about horizontal circles. We've talked about vertical circles. He's not going in a vertical circle. He's going to go in a conical pendulum. It's a cone, right? Yeah. Think of like an upside down cone. That sort of. Okay, so blah blah blah. Discussion. When an object travels at a constant speed along a circular path, we say that it has uniform circular motion. If its speed were changing, it would be its motion would not be uniform. Any object moving in a uniform circular motion is accelerated toward the center of its circular path. This acceleration is called centripetal acceleration and equals v squared over r, where v is the speed and r is the radius of the circular path. Since the net force at any object equals ma, during uniform circular motion, the net force, called centripetal force, equals mv squared over r, and is directed towards the center. This is what happens when an object suspended by a string moves in a circular path or a conical pendulum. The string of a conical pendulum sweeps out a right circular cone. In this experiment, you will measure the speed of an object that comprises the conical pendulum and show that the net force is mv squared over r. So even though, when the pig goes around a circle like this, even though he's attached up there, right, the circle is actually what? Horizontal. Right? And the force, what is supplying the force here? The string. There's a tension in the string supplying the force, but there's a component of that that's directed towards the center, and that's our centripetal force. The tension in the string is actually different from the centripetal force in this case. Alright, so pre-lab analysis. Draw the net force vectors of a free body diagram that acts on a conical pendulum. Ignoring air resistance, note that there are only two forces that act on the pendulum bob, in this case pig. Bob is another common name for a power pig. One is mg, the force due to gravity, the other is string tension T. So you've got that there, you've got that picture, and we need to draw in the components. So you've got T, pig. Thank you, Brandy. If this was university, you would have let him go on for at least 20 minutes before telling him. And it would have to get like that. All right, thanks, Brad. Okay, so we got the tension there. So label this one, it's already labeled for you, mg. So basically, you just need to draw in the components here of tension, and let's label those ty and tx. X being horizontal, y being vertical. Vectors is everywhere, man. You should write a song about Joey. A vector song. If you get hit. It's starting classrooms around now, though. Flip the page. Does the pig accelerate in the vertical direction? You want to see the pig fly, don't you? It's time. It's time. Now, without seeing it, yeah, I know. I'm just going to show you, if I just give it a push, he goes in a pretty good circle, and it does sway a little bit there, I have to sort of brace it, but the circle itself actually, like, is it getting smaller and smaller? It does, right? I can't explain it, but if I put the wings on, because he does have wings, see, you were disappointed, weren't you? But when the wings go, it actually stays, thank you, Joy, yeah. It actually stays in a pretty good circle for quite a while. Roger Waters would be impressed, wouldn't he, Joy? Okay, so, let's ask the question, does the pig accelerate in the vertical direction? Oh, he's dying, look at that. How much the new batteries in it? He's actually, the circle is getting smaller. Does the pig accelerate in the vertical direction? Surely it does. Did it change vertically? No, there's no directional change. It doesn't go up or down. It doesn't change its speed up or down or not. No, the answer is no. It does not accelerate in the vertical direction. What does that mean? So put no. And what does that mean? It means that ty is equal to mg, right? The vertical forces are balanced, right? There is no net force vertically. Step 4, does the pig accelerate in the horizontal or radial direction? Yes, his direction changes. Knowing that the net force in the radial direction for an object in uniform circular motion is the centripetal force, what does this tell you, about the magnitude of the horizontal component of T and mv squared over r? So the answer to step 4 is yes, it does. And it tells me that Tx, the horizontal component of the tension, is equal to the centripetal force mv squared over r. Step 5, write an equation that shows how the horizontal and vertical components of T are related to the weight and centripetal force. Huh? Well, there's a hint there. It says tan theta is opposite over adjacent. What is the opposite side if I let my theta be this angle here? Tx, and my adjacent would be my Ty, correct? And now let's substitute what we've just set those are equal to. So Tx is equal to mv squared over r, and I should have wrote that, sorry. Let's write it like this, mv squared over r, all over Ty is equal to mg. Fancy our algebra, what happens? Mass of pig does not matter. And what do you get? I wrote the m, didn't I? You get v squared over, or just rg, right? V squared over rg. Note, and that would be like brackets rg there at the bottom, right? Is equal to, let's write it over here. Tan theta is equal to v squared over rg. Okay, so that's what we're kind of working our way towards. Oh, and then step 6, you're supposed to algebraically solve for the tangential speed. So in other words, solve for v. So I'm going to take rg tan theta is equal to v squared. So v is the square root of rg tan theta. So in the actual lab itself, what we're going to do is we're going to actually find the speed of the pig, and we're going to see if it equals the square root of the radius times g times the tan theta. 2 problems. Can I come up with a value for g? Sure, 9.8. Can I come up with a value for the radius? How are we going to come up with a value for the radius of Floyd's circle?
Best guess.
Best guess. Well, I mean, we got to have some. A mile? A millimeter? Like, you know, like, we're going to need a little more accurate than that. I need a method, a procedure, some way to do that. Okay, so Jason is suggesting. But one thing we for sure can measure is length and strength. Shall we do that? If only Mr. Smigelski hadn't stolen my manuscript. And this one here too that I saved over here. Oh no, I got one. Okay. The length of the string has remained constant for about 8 years. I won't be surprised by the length. It's 80 centimeters. Okay, now what? Okay. How do I do that? Any ideas? No? Anyone else? Let's see what my notes say. I know what I'm doing, guys. I'm not totally. Let's read the procedure. Set the flying pig. Note that anything that flies in a circle works here, whether it be a toy airplane, toy flying pig, or flying cow, or whatever. You can actually get a flying pig hat with the wings that go like this. Did I tell you the story about the girl that asked if she could fly to warm up? She said, if I wear a hat, I can fly around the room? Yeah, that's what it means, yeah. And that's what everyone else in the room did. They laughed at it. Seriously. Be careful not to damage the delicate wings as you click them into their fixed wing position. Ask your instructor to check your pivot before switching on battery power. Carefully hold the pig by its body and give it a slight shove about 30 degrees from vertical, just enough so that the pig flies in a circle. The goal is to launch the pig tangent to the circle flight. It's better to launch it too easy than too hard. If the pig does not fly in a stable circle in 10 seconds or so, carefully grab it and launch it again. Once the pig is up and flying in a circle of constant radius, measure the radius of the circle as accurate as you can. Express your answer in meters. There are several ways to determine the angle the string makes with the vertical theta. Using a protractor may not be as practical as other methods you may devise. Describe your method and then record your value for theta. Include a sketch. And this is why we do it as a group, because we have a hard enough time as a group of 20 or so coming up with a method. So any bright ideas while I enjoy my morning beverage? But please don't just wait for me to come up with an answer. We have the length of the string. We would need the angle to determine the radius of the circle, right? Nobody? Come on. The first time I did it, I didn't know how to do it. I actually had to come up with a plan.
You can't stick a protractor on this.
No. We could weigh the pig, and what would that tell us? That would tell us the tension in the string when it's like that, right? How about if I just sort of take it, it's about an angle about like that or so. How about I just measure the string there, and then we'll just use the tangent. Does that work? Why not? Come on, think you guys.
It won't be that.
How long is the string here? How long is the string here? The length of the string is the same, you guys. Me putting it there doesn't make the string any, right? I raised it up. Well, the angle changes, but the height of the pig changes, right? So you can't use that length. The hypotenuse of the triangle is 80 gaps, right? We don't know what this length here is. We know what that length is, right? I guess I could do this, but I don't know if that's the angle that it travels at. That's
what I said.
right. How can I figure out how far away from the center it goes? Spin it and see where it goes. Does that give you any ideas, though?
Exactly 1 meter above the table.
What if there was some way that I could, I don't know, like put something up here, a stick or a string or something that, well, if it touched it, it wouldn't. Any ideas? You guys are so crazy. Let me see if I can find what I need here. Pardon me?
It makes an awful first period class.
Yeah? You might be familiar with these. You played with them when you were young, shining them in each other's eyes. Any ideas?
You find it and then place the dot as a marker?
Yeah, sort of. Okay. All right, I'll do it. This is why we don't do it as a group, or as a... How about I mark the spot directly below the table? Could we do that? Does that sound like something we could do?
Below the table?
Below the pig on the table. Someone's listening up there. Actually, I have a better idea than what I normally do now that I'm thinking here. Anyone know where I'm going with this? Hey?
Taking the table versus forward.
Could do that, right? So you're suggesting we hang the laser there, right? It's not bad, I never thought of that. It's too bad there wasn't a hook on the bottom of the foot. What, do you think, I think actually, the laser would actually do this though, I think, wouldn't it? Like, ideally, it would do what? It would hang straight down and it would mark that point. I think we should, eh? We could tape it, I don't know if that would.
If it points straight out, isn't it still the same thing?
Yeah, but I don't want the angle. What I really want to know is this distance, right? That's what I want to know. I don't, it's a good idea if we could devise a way that it would hang, and if I tape it, I don't think it's going to, I don't think I have enough here. Although if I had a little bit of chain on it, or string. There you go, I'm thinking. Yeah, I'm going to perform pace surgery. I don't think it's going to work. So appreciative of a grade 12 class. Do this in front, you don't have to keep them entertained every second. Do this, you know, whatever. They just sit and they just whatever, no problem.
I don't know.
What do you think?
That would swing with it,
Think
wouldn't
it's
it?
going to swing with it? Or do you think there's enough? I really don't have any idea. This is uncharted territory.
I think it would swing.
Well, we're going to try it. We're going to experiment. A true experiment is when you don't know what's going to happen. Does the weight matter?
No.
No, the weight doesn't matter. Remember, we cancel out M. So we have a brilliant idea, Mr. Smigal. You know the problem about being able to measure this, right? So Jason suggested we hang the laser, and that we're hoping that the laser will point straight down and mark the point on the finger. What do you think? It's a good idea, but is it going to work, do you think?
No, I think this would be leg because that's not a rigid string.
A chain might be better, right?
Just a bar that would be rigid because I think what's gonna happen.
But then it's gonna point out at an angle.
Like this.
Oh, because it's gonna lag. Well, there's only one way to find it.
It's like making it on
I think it's working, Joey says. Yeah, it's definitely going. Yeah. But it's still farther out. Like Anderson and I are, right? It's still farther out
It's so
than the pig, right? Actually, the pig itself is slowing down this for something else. And normally that doesn't happen. Okay, not a terrible idea, but. So instead of putting the laser down this way,
Shine it up.
and you'll notice actually, you know, what I've done in Mr. Smigalski's room, you can see marks on the ceiling where I've done it many times, and when I put the laser right here, and the kid always goes, oh, there's the mark on the ceiling already, because it's right there. Okay, yeah, so that's what I do, because I figure out where it is, and it's so much easier there because it's going right from the center of a cross in there, right? And I just put my laser here until it does what? Until it touches the pig, right? And then I just make the mark on the ceiling, then we got it done. Off we go. So,
You need ladders to do this?
no, I just kind of, but can I do it down, do you think? Like on here? Like, just basically, have someone, and come on over here. It was your idea. Go ahead. And I need something to stand up there, and actually you can stand on the table if you want. Okay, so you gotta hold, and unfortunately my battery, that thing is dying, right? So we gotta, does he really?
Yeah, he brags about it all the time.
He brags about it.
He's like, I have two now.
Visual.
He only has one now. It came with the check. Okay, so let's do this. Do you think maybe two would, I guess it's probably right? So, make a mark on the tape. That about right? Close enough? Okay. So now, yeah, go like this, right? You want to use this one? Yeah, it's got better battery. And basically, we got to move it left and right until the point that what? It's just, basically we see the pig cutting the beam, right? And you got to work from your right. And try not to get in the way of the pig. Bad circle, do you want me to try again? Come on. That's a good one, isn't it? Yeah. Okay. Okay, so is he in line with it there? Tell me when to mark it. You gotta go a little bit farther left. It's getting, the string is actually, I think that's good right there. I saw the laser on the body. Okay, so that's the length there. So our radius of our circle is 44 centimeters. The radius that I've got written down here is 52. Absolutely, I just realized it now. The radius that I have written down is 52. But we got to go with this because we're going to use our speed listener. So let's see what happens. Okay. So we've got what? What was it? 44. Okay. I've been talking so long, this thing disappeared here, right? Okay. So we're going to say radius is 0.44. How am I going to get the angle? Well, here now I can actually use, right? This is 0.44. The radius, the length of the string was 0.8 meters. And so now I can find theta by going, not inverse tan, inverse sine. 0.44 over 0.8. And you're going to have to help me because I'm going to have a different angle than I normally do. I get, ooh, that's not right. I get 33 degrees. Is that what you got?
Yep.
That seems about right, doesn't it? Okay, last year I got 47 degrees, so that's a considerable difference. So. Step 9, using the values for r and theta you determined in step 7-8, compute the theoretical speed of the pig using the formula you derived for speed in steps 5 and 6. So, our formula was v equals square root rg tan theta. So our theoretical speed is going to be radius 0.44 times gravity 9.8 times tan of 33. Okay? Does it negative matter? You don't want it to be negative here. How come? Because you're going to have a negative under the square root and then you're going to have a problem, right? And so it's just a value here. It's not a vector. 0.44 times 9.8 times 3310. I get 2.8. 2.8 what? Did I reroute that? 1.67, Peyton? Okay. Thank you. 1.67 meters per second. So that is our theoretical speed. So how can we find the actual speed? Well, that's what's in step number 10. Step 9, you calculated through theoretical speed. Now let's actually measure the speed of the pig and see how these two values for the speed compare. Since the pig flies in a circle, the speed is the circumference, 2 pi r, divided by the time for one complete revolution. To make your measurements of t more precise, measure the time it takes for the pig to make 10 revolutions and then divide by 10 like the previous example that we did. Right? So 2 pi r is our distance. 2 pi, the radius is 0.44. So I get a circumference of 2.76, and now we got to do time. That's the distance traveled, circumference, right? 2 pi r. It probably would be a good idea to have 2 or 3 people time, and then we'll take an average. Does that sound like a decent way to get it? Does anyone care if they time or not? That was a low battery. Anyone? Okay. Okay, so I'll spin it, and then we'll have to do it quick because the circle seems to be degrading, right? And I don't mean that it's making people feel bad, I mean that the circle gets fun. Now, what's one thing I have to do? I got to make sure that it's doing this again, right? Because if this is wrong, it's got to be the same. Will it always be the same angle? It isn't, right? We found that today, although usually I've had pretty good results as long as I sort of push it about the same. It'd be nice if you kept going, we could just time it in that. But. That's pretty good right there. Okay, so next time around, can you guys start timing? Ready?
Okay.
Oh, you're not ready yet? And 1, 2, 3, 4, 5, 6. He's definitely getting smaller. 7. Okay, we got it down. That didn't work as good. Can we just do 5, do you think?
I started a bit before.
You started at 4? Okay, so I'll do a better job of giving you the signal to go. How about we just do 5? Because I think that 10 is going to be too many. Okay, so I'll try to get it in a circle quick, and then I'll say start, and then I guess I got to wait once round before I said 1, right? I think I said 1 or... Okay. Okay, good. Are you ready? We're going to start and start. 1, 2, 3, 4, 5. Stop. Wednesday, I'm going to get mean. Jake, what was your time?
8.576.
8.57. Jason
8.2.
and Jason. What should we do? The person that doesn't want to pick up his calculator is just going to do this. And what's our time? 8.575? Are you good with that?
8.47 is the real average.
All right. I was trying to give you a little hint there. In university, I have to top this because I don't want to ever be... Okay, so there's our average. So what is the actual velocity then? Our time is 8.47. Our velocity is d over t, 1.67. No. d. 2.76 is our displacement. Time, 8.47. 2.76. Uh-oh. This isn't looking good, is it? That's not even close.
What do you get for 1 minute?
Oh, yeah.
Divided by 5.
Little mistake. Me too busy being an entertainer. The actual time, the actual period is 8.47 divided by 5, right? Thank you, Jason. You saved me. I was wondering what I was doing there. .69 seconds. So velocity, distance over time. Distance, let's get this right. 2.76. Time, 1.69. .63. Holy cow. I don't know if I've ever been that close before. So did we prove that for a conical pendulum, the net force is mv squared over r? A little more excitement, Jake.
Yes.
Yes, like, oh, look at that. We're like 4/100ths of a meter per second off. What's our percent error? A percent error, you don't even have to use a calculator to do the subtraction. It's 0.04 over 1.63. Percent error. .5% error. That's pretty close. Anything less than 10 is outstanding. Okay, and that's what step follows. Compute the percent difference between the value for the speed you computed and in step 9 and measure step 11, use the calculated speed as the note. That's what I did, 1.63. Yeah. So 2.5% is our percent error. Excellent. Okay, post-lab. What techniques for measuring R and theta would you recommend for the best results? I think we clearly nailed it today, right? So if you want to describe that, you can. Some way, in case you ever become high school physics teachers and you have to do the flying pig lab and you can't remember how to do it. You'll have it in your notes. And it's a flat lab. What can you conclude about the magnitude of the string tension compared with the weight of the pig? Oh, okay. This goes back to unit number 2. What can you tell me about the tension in the string compared to the weight of the pig? Is it greater, is it less, or is it the same? Like, the tension in the string right now when it's hanging straight up and down is equal to weight force, m times g, exactly. But what about when it's out here?
Always agree.
It's much greater, is it not? Because of the angle, right? This vertical component right here, Ty is equal to mg, right? But T has to be greater because of the angle. And in fact, as the angle gets greater and greater and greater, the tension becomes bigger and bigger and bigger, right? Try to pause there, let's write that in. number 3 asks, what do you conclude about the direction of the net force that keeps the flying pig in uniform circular motion? Well, the direction is, because it's a circle, the direction of the net force must be toward the center of the circle. Okay? It's centripetal. It must be towards the center of the circle. Question number 4 on the back page there. For uniform circular motion, the centripetal force will always be less than, the same as, or greater than the tension in the string. Well, the centripetal force is the Tx, is it not? So your answer should be the centripetal force will always be less than, same as, or greater than the tension in the string. Less than. It must be less than for that triangle, right? This line here has to be shorter than that line there, right? How does the pig overcome air friction or air resistance? I actually believe the wings cause some effect. I actually do. It's hard to believe. I thought they were just really for, entertainment value. But I actually think that over the years I've seen it swing without the wings going and with the wings going, and I actually think the wings somehow produce air friction. I don't know how. They're not like pushing back or anything like a bird would or anything. They're just basically like this just sort of copy the older bear. But it actually does seem to work. Okay. I don't know. Yeah, I really don't. I guess maybe they're pushing air out of the way, but I mean, you think that I would have to be like something out front that does that? I don't know. But yes, apparently the wings do something. List some sources of error. Well, clearly, how accurate was our measurement here? Well, I mean, it was reasonably accurate. We got pretty good calculated value, but that would certainly be a source of error. There's a timer source of error. I guess I may not have measured this very well. I guess you could also argue that the actual radius is not the length of the string. I only went to there. I guess you could argue that this distance here is actually to that very point, right? Because that's part of it, and it actually rotates. So I guess I maybe erred there. Our actual apparatus up here actually swings a little bit too, so there's some error there. Pig slows down, good point. And in fact, much more dramatic today. Normally it can go for like 2 minutes and it just keeps going. No problem at all. So I don't know what's going on, whether the wings are damaged, which could be there's a bit of a wrinkle in here, or it could be the battery too. I usually have the battery out, but I noticed that it was in this time. Okay, so there's the flying pig lab. You can all drop out now because that's what you've been waiting for, right? Everyone wants to play. All right, so you got the rest of the time if you need to work on something. Tomorrow we will talk about bank curves and such.